All right, so this is 2.3 part 2. We're talking about something called the ambiguous case. So we talked about the sine law in 2.3 part 1. Sorry, voice is a little bit scratchy this morning. So I'm going to talk a little bit quieter probably. We talked about sine law in part 1 and how we can, for triangles that aren't right triangles, that we can solve for sides and angles as long as we have an angle and its opposite side pair. If we're given that, or if we can determine that right away, we can use sine law. So the ambiguous case is a special situation where we don't really have that pair to start with. And so how do we know if we can even solve the triangle? So let me just talk about, it's up on the screen here. We talk about what the ambiguous case is. Let's just set it up. So when solving a triangle, we learned about solving a triangle. That's finding all the angles and all the sides. You must analyze the given information to determine if a solution exists. If you are given the measures of two angles and one side, then the triangle is uniquely defined. Okay, so listen carefully. If you've got two angles and one side, there's only one way that that triangle can be formed. Well, I shouldn't say that. It can be uniquely defined. However, if you are given two sides and an angle opposite of one of the sides, so SSA. So ASA looks like this, okay? You're given a triangle, and we have an angle, and we have a side, and we have another angle, okay? That's angle, side, angle. There's only one way you can do that triangle, okay? There's only one way. But if you're given this case where we have a side, and then a side, and then a third angle, side, side, and angle like this, now there's some question because these angles can be whatever and this side length can be whatever, and so there's some ambiguity there. So the ambiguous case comes from the term, the ambiguous means kind of like uncertain or unknown, almost like mysterious, like it's a bit ambiguous, it's not clear. Okay, that's what ambiguous means. So when you're given a certain set of information like this, and I'll just erase the ones we aren't given again. So if you're given something like this, like SSA, and I will not refer to it as the ASS triangle, okay, thank you very much. It's the SSA triangle, okay? Yeah, I've seen that in textbooks before. I'm like, why? You're dealing with teenagers here. This is a distraction. Anyways, so let's say that we're given this right here. So notice, guys, notice I am given a pair here. I am given an angle side pair, but I'm not given, I can use the sine law here because a side and an angle pair is given. I can, but the ambiguous case goes deeper than that. It basically asks you, can a triangle even be formed using this information? I'll explain that in a second. And if it can, how many triangles can be formed? And then you can go ahead and use the sine law. So even if we're given this important pair of angle and opposite side, the ambiguous case comes into play. We need to actually check a few things. So here's an example. Look at this one. Can you make a triangle with the given dimensions? So angle A is 55, side A is, so this is 55, this is 3, and side B is 6. Now what I've done, because we probably don't have protractors on you, this is what I did. So I've got a protractor on here, and I've got a solid line that I've started with, and what I'm going to do is I'm going to, on the screen here, if I can, hopefully this will line up like it did before. Okay, great. So here is my 6 centimeter line that is exactly, go from 0 all the way up to 55 degrees. So this is a 55 degree angle right here. Does everyone see that? So I'm going to just jot this down here. This is 55 degrees. Now the opposite side, okay, so we got 55. Well, let's start with this one. Side B, which would be this one, would be 6 centimeters long, okay, from here to here. Let's say that's 6. If that's 6, this little piece right here, this one, is 3. So we've got 55, and we've got 6, and we've got the opposite side has to be 3. Now notice something. If I do this, and I get rid of this protractor now, okay, let's just bring that down a bit. Notice what I have. And I'll label this one. This is 3 centimeters. Does a triangle exist with that set of data? The answer is no, because it's not a closed triangle. And you may be thinking, well, how is that even possible? Like, why can't you make a triangle? No big deal. Well, look at this. This angle has to be 55. If this angle was smaller, then we might have a triangle made. Look at this. If the angle was smaller, and this was 6 and this was 3, I could probably form a triangle. But with that angle being so big, it doesn't work. So this is sort of the root of the ambiguous case. You have to do some checking first. So this is the way I'm going to try and explain it, and I will need everyone to pay very close attention. So I appreciate those of you that are right now. Okay, now we'll go back to the textbook a little bit. And if you want to follow along, you can. Let's get to this section here. Well, my computer's taking some time to... Okay, calm now. Not good. Okay? This page right here, on page 105, okay, it starts to kind of dig into the ambiguous case. So notice that this right here was the situation that we had. About 55 degrees, about 6 centimeters, and about 3 centimeters. Okay, not exactly, but notice that there's no way that this side length can drop down and touch the base at all. So in this case, there's no triangle to be formed. So let's take a quick look into this a little bit further. Okay? So I'm going to put this in your notes, all right? And we're going to take a look at how we can kind of dig into this a bit. Okay. All right. So it should be noted that if you have an angle, like let's say this is 55 again, right, like we had, and this is 6, this opposite side, we were given it to be 3, but you can kind of see that, hey, there's a minimum length that this side would have to be in order to make a triangle. I'll say that again. In this opposite side, there's a minimum length, like what is the minimum length that this opposite side would have to be in order to just barely touch. If we were to swing this arm, like swing it like this, where would it just barely touch? Well, it would just barely touch at the shortest distance between this vertex and the baseline, which is forming a 90-degree angle. So the minimum length that we would be required, if we go back to this example, this minimum length here, the minimum, is where there's a right triangle or a perpendicular, a right triangle. Okay? And so how do we find that out? Well, the first step in deciding whether a triangle can be formed is we need to find out what the height is, or what this side length would have to be in order to form a right triangle. So if this was a right triangle, in order to find the minimum, this would be a SOHCAHTOA situation, right? Because it's a right triangle now. So really, I'm finding out what is the minimum length by doing this. The sine of 55 would have to equal opposite side, I don't know what that is, the minimum length, divided by hypotenuse. So if we multiply both sides by 6, this is the minimum length for this side. And so the shortcut is this. We have this length times the sine of this angle. See, look at that, B sine A. So I'm going to just highlight this right here. I'll rewrite it. But the minimum length, okay, TH, minimum length of opposite side of angle is B sine A, right here, where this is B and this is angle A. And this is the minimum length here to form a right triangle. Okay? So that's a lot of stuff, but your H, or your minimum length, can be found by multiplying B times sine of A. So let me erase some of this stuff so that's not as confusing for you here. And you want to write this down as note here. The minimum length of the opposite side of an angle is B sine A. And that's the minimum because it forms a right triangle. So if I go back to this right here, I'm going to copy this, I'm going to bring this down. Now we're going to evaluate this. We're going to use this information, And I'm going to say, okay, so my A is 55, right? The A is 55 here. The opposite side is 3. I want to check this to see if this is long enough to make a triangle. And so I'm going to use B, that's 6, times sine of 55 degrees. So what is 6 times sine of 55 degrees? 4.9. Okay, centimeters, because this is all centimeters. So guess what? The minimum length here is 4.9 centimeters. That's the minimum length required to actually close off this triangle. So this question right here, can you make a triangle with the given dimensions? The answer is no. No triangle can be made because B times sine A is greater than this, or this one is not long enough for the minimum requirement. So I'll give you a moment to digest that. And let me know if you have any questions. Okay, seeing no questions, I am going to say this, that I strongly advise when you're, I still do this when I'm looking at these questions. I either envision it or I sketch it out. I think you should sketch out every triangle in approximate proportions just to kind of see what you're looking at. So for example, if we had, let's do another example. I'm just going to alter this a little bit. So let's say we have 38 degrees here. Let's say that opposite side is not 3 anymore, but let's say it's 5. And let's say the original side here is 8. Okay. So you can write this down for example 2 if you want. But we are going to check to see if this how this works. So again, we're looking for the minimum requirement is B sine A. So I'm going to sketch this out. This is how you should do this. Okay, so I always draw a line on the bottom first, because this one, it doesn't matter how long this is. This is like side C or something. And then I go from here and I always kind of like sketch out what would be approximately 38 degrees. Doesn't have to be exact at all. But 45 would be halfway between 0 and 90, right? So 38 is going to be about here, I'm going to say. Let's just say. Side B is this side right here. So this is 8 centimeters. Okay? Now if this is 8, 5 is going to be about here, a little more than half. Please don't make that noise over there. So 5 is going to be a little bit more than half the length. Does that make sense? So look at, if this 5 centimeters got rolled down or rotated down from this vertex, it appears that probably we're going to have more than the minimum requirement to make this 90 degrees. Does everyone see that? You sketch it out right away and you're thinking, hey, that looks like I've met the minimum requirement. So what you would do is you would check. You would literally go 8 times sine of 38. And what is that? 8 times sine of 38. 4.9. Whoa, that's weird. Almost the same as the last example. So 4.9. So guess what, guys? 4.9 right here, this is the minimum side length to make an exact 90-degree angle. That's what that means. The minimum side length. So what do we have? We have more than that. Way more than that. Sorry, 5. Where am I at? 5. So not quite as long as I've exaggerated here, but it's a little bit longer. The 5 is a little bit longer than the 4.9, right? So does everyone kind of see that, yes, a triangle can be made with this, because this opposite side is greater than the minimum requirement. Now, this actually gives us another situation that we need to carefully look at, in that, so if we do have a side length that is longer, so let's say it's about this long, then actually 2 triangles can be made in this case. Here's what I mean. Watch this. We could have a triangle that has 5 centimeters like this. And you could now have this triangle that I'm highlighting in blue. Everyone see that triangle? You could not only have that triangle. Okay, I'm going to try and copy this here. You could not only have that triangle. Oops. Sorry. Copy, not move. Okay? But you could also have, watch this, this is so cool. To me, this is cool. To you guys, you're thinking this is not cool, maybe. But look at, you can have 5 centimeters over here. That's the worst line ever. But look at, you see, we have all of the same requirements met. So in this case, we could uniquely create 2 separate triangles with all of the requirements, or with all of the dimensions that are given. Does that make sense? So sometimes we can have 2 triangles. So we could have no triangles if that opposite side does not meet the minimum requirement. We could have exactly 1 where the opposite side is exactly the minimum requirement. We could also have 2 triangles made. Okay? So here's another one to think about. What if this wasn't 5 anymore? And this will be example 3, but I'm cheating because I'm just copying this here, right? I'm sorry, you guys can't just click and copy your notes there, but. So let's make this one, ready for this? 10 centimeters. Is this possible? Take one moment and sketch this triangle and tell me if 0, 1, or 2 triangles can be made using this. So take 30 seconds, sketch it out in approximate proportions, and let me know what kind of triangle you have. Okay, so this is how I would attack this. Again, I would sketch it out. Side B, remember this is 38, so side B is 8 here. And side A is 10. Wow, that's even longer than this B side. So guess what? Your triangle would look literally something like this. And there would be 1 triangle being able to be made, not 2. Okay? So, as bad as this line is, let me see, I can't actually. Okay. So let me just watch this. I think this should work well. Sorry. But if I had this is the 10 centimeter line right here, okay? Now, why can 2 triangles not be made? Well, because of this. If I were to actually keep this same length and swing this triangle around, do you see how it wouldn't touch the baseline anywhere else? It would miss it over here. So you swing it around and it only touches in one spot right here. 10. Okay? So back up here, the 5, okay, let me just do this now. Back that up. I'm going to make this a line, okay, like this. So the 5 here, oops. See if we can get that landing sort of there. So look at, if I take this and I swing this around, literally it can hit the baseline in 2 spots. One there, and one over here. See that? So we're going to summarize all this in a second. But I just kind of want you to see visually, and I want you to see how, the minimum requirement here we know is 4.9. So 10 is greater than 4.9, but 10 is also greater than B. So that's 1 triangle only. Okay? All right, so let's go back to the text. Oh, shoot, do I have the text here? I thought I tried to open this here. Open. Oh, there we go. Okay. So, this is what's in your textbook. So let me try and summarize this, okay? So this one here, if A is less than B times sine of angle A, then there's no triangle form, no solution there. If A equals, right here, if A equals B sine A, then it forms 1 triangle, and that's a 90-degree triangle, a right triangle. If, guys, boys, if A is greater than H, or greater than B sine A, and less than B, we could have 2 triangles, so that's this one. A is greater than H, but less than B, we could have 2 solutions. And if A, this opposite side, is greater than B, then we have 1 solution. So this is the ambiguous case. These are the options right here. These are all of the options. I'll clip them into our notes, and we'll do some examples. Okay? So, move down, down, down. Okay. So these are the options, and I will highlight for you the fact that if the opposite side is less than the length of B times the sine of A, we have no solution. This would be good to copy down into your notes, I suppose. If A equals B sine A, then we have one solution, and it's a right triangle. Okay. If A is greater than B, so this one is bigger than this side, then we only have one solution, looking like this, because it doesn't touch over here on the baseline ahead of A. And then here's the big one where you have two triangles, the only option. If the opposite side is greater than B sine A but less than B at the same time, then there's two solutions, or two triangles that can be formed. So as you just take down those, jot those down into your notes, this is the essence of the ambiguous case. It's kind of like, can a triangle be formed? If yes, how many? And then you're going to be asked to solve the triangle or triangles that can be made. That's what this second part of 2.3 is about. So if there's two triangles, you have to draw them separately and solve the different side lengths and angles. So there'll be some differences. Okay? So we'll do an example here. Okay, so we're going to do this one example before this lesson is done. So let's do this one together. It says this: in triangle ABC, angle A is 30, side A is 24, and side B is 42. Determine the measures of the other side and angles. Round your answers to the nearest unit. Okay, first of all, let's sketch it out. Step one, sketch, right? So for a solution, step one, we're going to sketch it out. So it doesn't matter how long this bottom one is. Just draw a straight line. Roughly estimate a 30-degree angle and make this B side 42. Now A is 24. That's almost half. So right now we don't know where 24 lands. Is it long enough to form a triangle? Don't know. So what do we need to do? We need to look at B times sine of A. And so right away you go 42 times sine of 30. And this is going to represent the minimum requirement here. We don't know about 24. This is going to represent the minimum length required for a right triangle. So what is that? 42 times sine of 30. 21. Okay, so 21 is the minimum requirement. Right here, 21. What is the side length that's given? 24. So we have at least one triangle. How many triangles do we actually have if this is 24? So since B sine A and B, so since the H, the height of the triangle, or I should say this one's right, since A is greater than B sine A, this is the minimum length required, and A is also less than B, then we have two triangles. And this is what they would kind of look like here. 30 degrees, 24, 42, 30. There's triangle 1. And triangle 2 would look something like this. (24), 42, and 30. Does everyone see that? So here's your minimum requirement that we calculated to be 21, and here's your minimum requirement over here in this one. So two triangles. Got it? Now what we need to do is we need to solve for the missing sides and angles. This is where it takes a bit of time, but I mean once you kind of get rolling, it's not a big deal. So I'm going to erase some of this and let's tackle this together. Okay? So you can just watch, or you can write this down. It is in your textbook. I might not do it exactly the same way, but let's give it a go here. Okay. So let's do the solution for number 1. Okay. So for triangle number 1. Let's try and find, let's see, this was A, right? This is angle B, this is angle C. So what do you want to find first? Well, let's find angle B first, because we have sine of 30 over 24 equals sine of b over what?
42.
Over 42. Thank you. So I'm going to cross multiply. Sine of b is actually going to be equal to 42 times sine 30 over 24. I'm going to take the inverse of sine of all this, of both sides, and that's going to give me angle B. Okay? So if we go ahead and do that on your calculator, you should have this angle B being about 61 degrees, okay? So this on your, make sure you can do this on your calculator, should give you 61.044 or something. Okay? Does that look reasonable? Wait a minute. That does not look reasonable to me. Why not? Now this is very important. Watch this. Very, very important. Do you see what I just did here? I put 61 right here. That does not look right, does it? This angle should be obtuse. It should be greater than 90. So guess what? When we solve for an angle, our calculator is always going to give us an acute angle solution. Always. So this is why I really like the diagrams. Guess what? This is 61. Right there. That is 61 because we've used all of the same numbers, notice. So how do I find this angle? This is not 61. What would this be? Any ideas? 61 would be the reference angle for this one. Remember we learned about reference angle last week? So if 61 is the reference angle, what is the actual angle if it's between 0 and 180? It would be 180 minus 61. So that's going to be 119 degrees. Wow, your mind blown yet? Okay. So there's a few things here. There's a few things that line up here, isn't there? Okay. So 61, great. That actually goes for number 2. So now it's fairly easy, guys, and I think you guys could probably do the rest of this on your own. Now that you have this, it's just sine law, really. This one you can find the third angle, so can here find the third angle, and then use sine law to find this side, right? And sine law to find this side. So I'll give you the answers here. If this is something you're unsure about doing, you can just go ahead and do this, and I'll give you the answers here. So as in your textbook, we should have angle C up here is 31 degrees. This one here, angle C, and this one is 89. And these opposite sides are going to be, this is going to be 25, and this one's going to be, looks like 48. Okay, so those are the missing sides and angles if you want to test out the rest of that. But I think you've got enough information that you can do that. All right, any questions? Okay, so take a moment to look at the key ideas. You should have everything you need to know now about this section, so I'll add on to your homework in a minute. So once again, guys, here's your complete assignment. You should have done 1 to 4 already. You got 1 to 5, 8, 10, and 13 is optional. Here are the questions again if you need it. I'll show on the video. 1 to 5, 8, 10, and 13.